It's working? Okay. Do you want to introduce me again?
Do we do that again? I mean, did we lose it last time, or can we?
It's unclear.
It's fine with me.
I think Michelle
Yeah,
can
man.
edit it, but.
Okay.
Hello, I'm Judd Taylor with the Atlanta Functional Programming Meetup, and tonight we're happy to have Daniel Cartwright of Level 3 Communications. Is that right? Cut. Layered through.
Careful with my Ethernet cable. You're about to trip on it.
Layer.
It doesn't
Just-
say it on there. I thought it did.
No, it doesn't.
I thought I put it on.
Yeah, I thought you were being humble. Hi, I'm Judd Taylor with the Atlanta Functional Programming Meetup, and tonight we have Daniel Cartwright of Layer 3 Communications, and he's going to give a talk called Property Testing with Hedgehog, Eating Your Bugs. So, to you, Daniel.
Thanks, Judd. How many of you are familiar with property testing? Okay, 2 people. I'm gonna give a talk about property testing, and toward the middle, we'll start focusing on how you can do property testing with Hedgehog, which is a Haskell library, which also has an F# port, and I'll also talk about how you can do property testing in various languages and the libraries that are available for doing it. While there are many ports of this stuff, it's pretty unknown by a lot of programmers, so I think it'll be really useful. So the talk's going to be divided into 3 main parts. I'm going to talk about what property testing is. Then I'm going to talk about approaches to property testing. And then near the end, I'm going to show actual code that uses property testing that you might actually want to use in real life. So what is property testing? I often like to explain things with motivations for why they should exist, and I like to start with motivations. So let's look at a problem with testing. So often when you're testing software, you have to determine how expensive would it be for this code to break. If this code breaks, do we lose money? Do we lose developer time, which translates to money? You have to evaluate these things. You also have to think about the proper tooling, the proper programming language and build system that gives your developers the comfort and ease of testing that is effective. There are several types of testing, and you do need to determine what they are. For example, what they are and what you need. For example, you may not need formal verification. For those of you who doesn't know what formal verification is. Okay, so formal verification is where someone will take some kind of theorem prover and encode the logic of your code in it and verify that it is correct. They will produce a mathematical proof that your code is correct under certain invariants. So that's what formal verification is. It's very costly, it takes a lot of time, and there's not a lot of people in the world who can do it. So most of the time you don't need that. Most of the time people resort to what are called unit tests. And these are extremely common. Here's an example of a unit test in HSpec. HSpec is a Haskell library for doing unit testing, and you have my assertion, which has the type assertion, and it reads, my function applied to example input should be expected output. So we can see that the definition of a unit test, which I'm sure many of you already know this, but it's best to be clear, a test that checks whether the output of a function for a single example is equal to the expected output. But there are problems with this. So there's the coverage problem. So how do you cover all code paths? In real code, a lot of times there's too large of a state space for you to be able to, as a human, enumerate them in code. A unit test is essentially a developer picking out inputs and outputs and matching them together and saying, this is what I expect for this input. And that's very costly. So that's the other thing. There's developer cost. Cost a lot of developer time. The other thing is that unit tests are not fun to write. So test suites are very, very frequently the most sloppy, hastily written code in any code base, because people don't like writing them. They want to write code that actually does stuff, and testing is most of the time an afterthought. Property testing as a solution to the coverage problem. This is probably the most compelling reason to use property tests. So property testing differs from unit testing in that it is parametric in its input. So programmers don't supply explicit inputs. And instead of saying, for this input, I should get this output, what you say is, I expect my code to adhere to a certain property, and you never manually construct the input. The key difference is this third one. The inputs are generated, so these are generative tests. They're not, inputs are not supplied by humans. A good question then is, how do you generate these inputs? Well, it depends on, what kind of test you're running. So there are exhaustive property tests, which means that you want to test for every possible input. And of course, for a lot of types, this just isn't possible. You can't test every possible string. You can't test every possible, int, 64-bit integer. You can, but it would take a really long time. There are also randomized property tests. So instead of being exhaustive, you take your state space and you pick out random bits and pieces. So you randomly sample whatever the space of your input is, and then do that. And that's often a much more efficient way of approximating exhaustive property tests. And then there are exhaustive specialized property tests. Specialized is a little vague here, but basically what it refers to is you pick a subset of your input space, and it's the exact same as the exhaustive property test, right? Like you enumerate the whole thing, but you're just doing a subset of it. And randomized specialized ones are, where you have a subset, but it's randomly generated. Does that make sense? Any questions? Okay. So this would be an example of a property test. This is actually like a canonical example. So this function, properverse, takes as input a list of characters and outputs a bool. So what we're checking here is that if we reverse we reverse the list of characters, I'll just say a list of characters is a string. We reverse the string, and then we reverse it again, we should get the original string back. Okay, so that's just an example. So in order to talk about property testing, writing good generators and understanding how generators work is actually pretty essential. So most of the time, generators are, have some sort of randomness. So because most input spaces are too large to do anything but randomly generate data, it's often the most useful. So a generator is actually a value that when you when you sample from it, it describes how when you sample from it, you should get some value of the type that the generator specifies. So, and there's also a discipline to writing good generators. If you write bad generators, you could actually end up not finding bugs, which is obviously not what you want. Typically, good generators generate, they randomly select from as much of the state space as possible, but there are also instances where you don't want that to happen, where you want a constrained state space. So, and like I said, not all types are easy to generate. So, for example, an 8-bit machine word, you can enumerate that very easily. But a string, you cannot enumerate all inhabitants of the string type. And this is a really important one. Generators can often be constructed using combinators. So you have small functions to construct generators, and you can compose them to create bigger, more complicated generators. And you can do things like filtering, applying sizing invariants to generators, things like that. So here's an example where a bad generator could fail. So again, assuming that you want this to succeed, if you have a generator that just generates a list of a random size, this will only succeed if the generator produces lists that are less than 100 elements in size. So if you were to supply a generator that generated a list from size 0 to 10,000, it's very likely that this would fail. It's a pretty trivial example, but we'll get more into more complicated examples in a little bit. The other part to property testing is called shrinking, and to me this is the more interesting one, because there's a lot of ways you can do it, and there's a lot of thought that you have to put into it. So you have to consider what happens when a property test fails. So when a property test fails, obviously the testing library has the value that it failed with. But if we are dealing with something like a data structure, the counterexample, the thing it failed on, can be pretty large. So printing that to standard out or standard error or whatever can actually end up being more confusing because it's so large. The developer's like, well, that's a big blob of text. I don't really understand what the problem is. So shrinking is a way of taking counterexamples and minimizing them to show a very small case where the same generator would still fail for the property. So here's an example where this is actually useful. And it's a really simple function, but it could be hard to see why it fails at first. So again, you have a string, and you're trying to see if all the characters in the string are lowercase. So this property says, after I convert all the characters to lowercase, all of them should be lowercase. Well, the problem is, if your generator includes all ASCII characters, there are a lot of characters in ASCII that cannot be converted to lowercase, like numbers. So a counterexample that your generator might come up with is this gobbledygook string, and then it might actually end up shrinking that down to 1. And this is a pretty minimal counterexample because the string 1, if you were to say if all of the characters in the singleton string with just 1 in it is lowercase, then obviously that's false because numbers can't be lowercase. An important thing to note is that the shrunken counterexample 1 is not necessarily part of the original counterexample. Which sort of brings me to my next point. Shrinking with invariants. This is a very important thought when it comes to shrinking. So shrunk values must have been able to come from the generator that generated the original value. This is really important. So consider this is like pseudocode, more mathy, but consider like the following pseudocodish property. For all n, we're saying n is a number. For all n, where n is greater than 6, this implies that n is greater than 5 and n is odd. The problem with this is that, say you generate a random integer and it ends up being 8. Well, if let's assume that the left-hand side here describes what the generator could generate. So the generator only produces integers greater than 6. So let's say that the generator created 8, so 8 is greater than 5, but it's not odd. So if we didn't shrink with invariance and we allowed values that the generator could not have produced itself, we could shrink to a number like 0. Shrinking integers towards 0 is very common because it often just makes values smaller and easier to think about. But in this case, it would be incorrect behavior because the generator could not have like produced a value of type 0. So this error message is kind of cut off because I screwed up. But if you were to run this sort of like, this is pseudocode again, but if you were to run something like this and you had a broken shrinker, it would say, it failed, the following number larger than 6 did not pass the test, and it would say 0. And you would be really confused because 0 is not larger than 6. So something important about shrinking. Do you have any questions?
So that your pseudo error message, it's not larger.
Yeah, it's
but
cut
only
off.
The error is actually that the generator could not, it's tested something that could not have been, okay, that makes sense. So the error message doesn't take into consideration the definition of the generator.
Yeah, so the error message is actually indicative of a worse problem, which is that the shrinking mechanism did not pay attention to, like, it didn't respect the generator that actually generated the data, which results in worse error messages. And obviously worse nonsensical error messages are not what you want in a test suite. You want the purpose of your test suite is so that you see errors that help you fix the problem.
There was a question from online. So are generators equivalent to fuzzers in security testing?
Sort of. So my interpretation of a fuzzer, I'm not like a security expert or anything, but my interpretation of a fuzzer is that they'll generate like random instructions and run those. So I definitely think that you could use generators for that. Actually, I think that might be a pretty good application thereof. So yeah, if you had an interpreter, there's actually an example I wanted to show, which was an implementation of the simply typed lambda calculus. Both Lisp and Haskell are built on top of some simpler lambda calculi. So and it had, I didn't finish it, but it had like it was very short, but it had like a full type checker and parser, and it was going to show that if you generated random well-typed expressions and then type checked them and then did all this parsing and crap, and then did the inverse operation, you'd get the same data back. So yeah, I definitely think that fuzzers could be an application, though I haven't seen anything like that. After you said that, though, that did remind me of a friend who had talked about doing something like that before, but I don't know a lot about fuzzers, so. Okay, any further questions? Okay. So, is everyone clear on what property testing is? Instead of writing explicit inputs and outputs, you talk about properties, and then properties that apply to certain inputs, and then you provide a way to generate those inputs, and it will just test those by running the generator and producing a bunch of random inputs. Okay, makes sense. So I'm going to talk about approaches to property testing. Property testing is a pretty old idea, as old as, sometime in the 90s. And I'll talk about that in a second. As old as the 90s, but it still hasn't really caught on. I'm not sure why. I think it may be like a similar phenomenon to just like things in functional programming take a really long time to overtake the mainstream. But I digress. So I'm gonna, sort of briefly mention a bunch of libraries for various, languages, in which, which provide property testing. So you can probably look at these, but C has theft, C++ has CPP QuickCheck, Clojure has test.check, Common Lisp CL-QuickCheck, Coq has QuickCheck. Erlang is actually very interesting. Historical tidbit. So the original QuickCheck, I think, was written in Erlang. I could be wrong, but one of the very first versions for sure was written in Erlang. And when they were writing QuickCheck version 2, they were writing versions for Erlang and Haskell, concurrently. But the guys who wrote QuickCheck 1.0 said, we're going to close source this and charge a bunch of money for it because it seems like something people really want. And the Haskell community said, if you do that, we will fork it and we will make a better version. We will make our own version 2 because it's open source right now. So legally, you can't, pursue us for any wrongdoing. Erlang actually the Erlang community did not do any such thing like the Haskell community. So QuickCheck 2.0 in Erlang actually is proprietary, closed source, and costs a lot of money. So if I was an Erlang shop, I'd probably pay because it's a really good library. But I don't write Erlang, so maybe if I work at Cisco one day. But so F# has FSCheck, and it actually has first-class support for Hedgehog. The Hedgehog team concurrently maintains the Haskell and F# variants of Hedgehog. And we'll talk about QuickCheck and Hedgehog and the differences later. So Golang has Gopter and Quick. And Haskell has the most of any. And that's just a few of them. There are actually more, but these are the most well-known. QuickCheck, Hedgehog, Validity, and SmallCheck. I'll talk a lot more in depth about the differences between QuickCheck and Hedgehog. I actually don't have a lot of experience with Validity, so I won't be discussing it. But SmallCheck is an interesting case. So the name kind of gives a hint. So SmallCheck is actually really good. It's much better at testing when you can fully enumerate the state space. But that's the only time it's useful. If you can check every single input possible, that's when it's good. Otherwise you should not use it. So Java, JavaScript, PHP, Python, Ruby, Rust, Scala, and Swift. Rust actually has a QuickCheck port. That's important, and Scala check is supposed to be really, really good. And Hypothesis from Python, of all languages, surprisingly is supposed to be very, very good. It's actually a pretty decently popular library. But these are just some examples. Whatever language you typically write, recreationally or professionally, maybe you want to take a look after this talk. So now I'm going to talk about QuickCheck, and then I'm going to talk about Hedgehog. So QuickCheck is pretty old. Started in the 90s. That was version 1.0. Version 2.0, I don't know when that came out, maybe late 2000s, early 2010s. It was a while ago. But even though it's old, it's a really good library. Really well engineered, fast, very well thought out. So it was pretty much the pioneer of randomized property testing. It was like the first, at least popular thing to do that. I'm pretty sure that it was the first thing to do that because the guy who wrote a paper on it. it uses the arbitrary type class for things that can be generated. And it's probably the most integral part of the API. So for those of you who aren't familiar, does everybody know what a type class is? Sort of like an interface, similar to that. The arbitrary type class parameterizes one type A, and it has two type class methods. It has arbitrary, which has type gen A, which you can guess is a way to actually generate values of type A. And then it has a shrink function that takes an A and produces a list of A's. And the idea behind the shrink function is that you produce, you take one A and you produce a bunch of A's that are, consecutively smaller, in shrinking terms than the A that you gave it. And then the testable type class for things that are testable. Like those are things that you can actually run the QuickCheck function on. So things like bool functions actually have a testable instance if their argument has arbitrary instances. So you can pass for example, in this example right here, you see that. So QuickCheck, and then you're passing it a function who has one argument, which is a string, and strings have an arbitrary instance. So this will actually generate a random string and then check that if you reverse it and then you reverse it again, you'll get the original string back. And then that would just say, passed 100 tests or whatever the default is. Is everybody clear on arbitrary? Does that make sense to everyone?
Where in arbitrary would you say that, okay, if it's a string, the arbitrary of string is X? Or how do you get an arbitrary string from, you say, I want an arbitrary string. What generates
the thing to keep in mind is that class instances are separate from class definitions. So this is just the definition of the class, and the actual implementation of various instances is separate.
Sure, so there'd be some, where string or whatever.
There would be an instance arbitrary string where, and then you would define the instance, like you would define the methods there.
Okay, and is there there must be by now a lot of kind of well designed or well tested generators for these arbitrary strings or whatever.
A lot of the data types have that are in the standard libraries have very sensible defaults that should be good enough for most people. There are problems with centering your API around a type class where you lock people into one, which we'll talk about later.
So for a string, can you define how large the string is, or?
Yeah. So it's actually really important with things like that because you have to you need to define some size range. Hedgehog makes this a lot more explicit with a range data type, which just has two ints or whatever in it. But in QuickCheck, this is a little less apparent. But it is still there and available to you. So good question. Do you have any other questions?
I think you'll probably touch on it later, but I just want to, so say that you have something that is basically, I'm not getting my Haskell terminology right, a subclass of string that is that you have some data type that's the set of all last names of anyone at this university, right? So those are strings, but they're not all strings, right? So there's some, that would just be a list of, you could enumerate all of those, but you can think of a case where.
So are you thinking of a case where you have all of those available to you? Say you have say you're working at a university, you have a database with people in it, and you have all of their last names.
That was perhaps a weak one, but let's say they have some other, I don't know, for credit cards, right? They have a quick a sum, checksum. Right?
Yeah.
So something like that, where the number of possible cases is huge, but the set of all true cases or valid cases is also huge, but much less huge than the first one, right? So I don't want to go ahead and enumerate all the possible valid cases, but I know that it's not as large as this larger case, right?
Yeah.
Does that make sense? So if I
That's
had some set of strings or some way to generate strings, which would generate perhaps an infinitely large set of them, but not all of the ones that could be generated by string itself, right? Is there how?
so yeah, that actually ties into a problem with with centering your API around the arbitrary type class, because you know there's only one instance for string, right? But what if you want it to differ? I'm actually going to touch on that, but the short answer is that you with QuickCheck at least you need to new type wrap a string and give that an arbitrary instance that matches the sort of generative properties that you're expecting. Writing good generators is one of the most integral parts of actually using property testing libraries. And it's certainly a lot, it takes longer than writing a single unit test, but it is way more worthwhile. So I'll cover I'll cover the answer to your question in more in depth in a little bit, but that is a good question. Do we have any other questions? Okay. Oops. So do you guys know what, does anybody know, does anybody not know what reflexivity is? So reflexivity, let's say you have a binary, a binary operator that takes, for some type A, you apply it to two A's and the output is a bool. Reflexivity means that, let's say f is the binary operator, takes two inputs, fxy equals true. If that's the case, fxx. So if you apply the binary operator where both of its arguments are itself and it's true, then that means the operation is reflexive. So you can actually see that in this reflexive function. So over here we have a constraint that A must be arbitrary, and then as an argument it takes a function from A to bool. So it takes two A's and outputs a bool. And then recall that we have a testable instance for functions if the input is arbitrary. So we know this A here, which is this X, it has an arbitrary instance. So whenever we actually run this reflexive test, it will generate a random A value and fill it in for X. And this says that X, like rel applied to X and X must be true in order for this property to be true. So, excuse me. Does that make sense to everyone?
Well, yeah, okay. Your second one, the reflexive rel equals lambda x for x rel x. So if and only if x rel xx is true, it's going to be true. Otherwise, it's false.
Yeah.
Okay.
And the way the testable type class works, because that returns a bool, then like bool has a property instance. So bool will it will fail the property if it's false. So if it's false, your property fails. If it's true, your property succeeds. Okay. This looks nice, but there's actually kind of a problem that you start to notice when you're using QuickCheck. And most of the time you can work around it, but they're there. And the two biggest property testing libraries, QuickCheck and Hedgehog, they both have various trade-offs that I'm going to discuss throughout the talk. So this combinator can only test reflexivity of a given binary relation if the relation is reflexive for all possible values that can be generated by the arbitrary generator. So what that means is that because we've locked down the A using the arbitrary A constraint, then that means in order to provide like a new generator, like a different type. Say, like for example, we wanted to test like a subset of strings that we are, we're way more constrained in the state space. Um, you you can't do that as easily. You have to create a new type every time. You have to create a wrapper type and give it its own arbitrary instance. Um, and this is actually a real problem with things like rational. So, you guys familiar with rational numbers? Basically, a fraction. It's just got like a numerator and a denominator. So its eq instance assumes that the values are normalized. So this expression here, 2 over 2 double equals 1 over 1. To a human, this is obviously true. But like its eq instance does not normalize the values before comparing them. It will just compare them, raw, without any manipulation. So that's a big problem because, even though these may be equal, the eq instance for a rational may end up saying that equality on rational numbers is not reflexive, which is obviously false. I know that was kind of a lot, but does that make sense?
Yeah. So what would you do then? Can you define a test for, you're gonna take eq and then do something to it to say like, okay, first I want you to normalize these things and then.
So I'm actually going to talk about that. But that is a good question. That is the correct line of thought. So this introduces us to some problems. Arbitrary is lawless. So that's the first. Some people may not have a problem with this, but in Haskell, I typically am in favor of type classes that have laws. And what it means for a type class to have laws is that an instance of this type class must obey certain invariants. And this is actually very useful because it allows us to design APIs around type classes, generic programming, which is how you do, generic programming in Haskell, while understanding that this function will obey these invariants, which is very useful for things like monoids, where you're building up things associatively. So there are obviously a ton of type classes, but understanding the behavior of how a function will work based on its type signature is a very powerful thing. The other thing is lawless type classes don't have any clear semantics. So it's not really clear like how you should implement an arbitrary instance for a certain value. So how should we implement the arbitrary instance for rational? Well, there's a lot of considerations. Should we ever let it generate 0 over 0? How about 1 over 0 or n over 0, whatever n is? How about 5 over negative 1? How about negative 5 over 1? Should we take some sized parameter into account? And also, if you never generate an unnormalized value, then we could fail to test edge cases that fail to handle unnormalized rationals. And if you only generate unnormalized values, that means we can't test properties that require equality to work properly, which is the problem we were having with reflexive. So the typical solution is to have a new type wrapper around all of your types. So for example, if we only want positive numbers, there's a new type wrapper called positive, and it wraps any number, a type, and it will ensure that you're generating a positive number. I'd say that in every test suite I've ever used with QuickCheck, I've had to wrap certain things in new types to actually, just for arbitrary instances. And it can become a little tedious keeping track of all of them, especially in larger test suites. So there are more limitations to this, which I'm going to talk about. Generators in shrinking are expensive. So every time you need to write a new generator, that costs developer time. It's time spent, not testing and writing code that allows you to test. And of course, maybe this isn't so bad in small enough test suites, but it can get bad. I'd say the worst thing is, the worst one is shrinking, which I'll get to in a second. So in QuickCheck, the documentation actually says there's no generic arbitrary implementation included because we don't know how to make a high quality one, which is actually a problem that Hedgehog sort of addresses. And I don't really blame them because it's actually really hard to have like a generic like default way to generate data that actually makes sense. That would require something very sophisticated, and I don't know what it would look like. So yeah, there's no default implementation of arbitrary, so you have to write it. And with the new type thing that we just talked about, where your test suites have to be, sort of riddled with new types, you have to write them for every single type. And one of the reasons that, I think shrinking is an even worse example is that the default implementation of shrink is const empty list. Recall that the type signature of shrink, it takes an A, gives you a list of A's. Const is the combinator that it ignores its second argument. So const empty list X will always be the empty list. What that means, and Hedgehog treats an empty list as do not shrink this value because there are no consecutively shrunk values. So this means that by default values are never shrunk. You have to provide your own shrinking, and this is actually another thing that makes this statistically bad is that most developers of QuickCheck do not actually write shrinks. So their errors can actually be pretty bad when their data structures are really large. And shrinking is often a lot more difficult to implement than generating, which costs developer time. And I said this in the beginning, but test code is already among like the most unenjoyable, sloppy, hastily written code in most any code base. So making your test suites even more annoying to write, even more unenjoyable, is not a good thing. That's something you want to minimize. And this is sort of a Haskell specific thing. This exists in other languages, but orphan instances. Often the way type classes work in Haskell, instances by default either need to exist in the same module as the type class or is in the same module as the type itself. And when you don't define instances elsewhere, instances are global and they are implicitly imported, and there's no way to sort of deny those instances from an import. So if you, say I define an instance in a module, and then I don't really, you don't really know about it, and then you import that module, there's no way for you to control whether or not that instance affects your code or not, except by not importing that module at all. So this leads to what's called the orphan instance problem, where you have to create orphans that are sort of pervasive. So there's no escaping them.
If you try to define, in the case that if you try to import something and then import something with the same ID or whatever,
You'll get a conflicting instance.
Okay, well at least then you have an error.
Yeah, you have an error. Yeah, because type class instances are sort of global.
Right.
You can only have one type class instance for a given type.
Sure. And then if you try to define something for the type that sort of tries to override it.
Yeah, which is why you need to have a new type wrapper.
And then you have this, again, as you say, riddle.
Yeah.
You have to riddle it yourself.
You have a lot of new types. So those are some of the problems with QuickCheck. Hedgehog is a really new approach to property testing. So this is almost like 20 years after QuickCheck. It's by a really nice guy, really smart too, named Jacob Stanley. And this is an example of the same property test that tests, whether or not if you reverse a list and then reverse it again, you get back the same list. And you notice there's no, I'll kind of go through what this means in a second, but gen.list takes, is a function that takes a range of int and then a generator for some type A and produces a list of some range that it picks in between whatever range that you have. So range.linear says my range is any number from 0 to 100. And what it will do is it will, let's say I get 85. Say it randomly picks 85. It'll generate 85 different alphanumeric characters. And then, actually, I don't remember if that's alphanumeric. It might just be alphabetic, but it'll generate 85 random characters and then, shove those in a list. And then it will check that property. So instead of type classes, you're just dealing with raw values. So you avoid all of the problems that we were just talking about with arbitrary. Okay. Does anybody have any questions there? Nothing too deep into Hedgehog yet, just, okay. So Hedgehog differs from QuickCheck in several ways. You get shrinking for free, so you don't have to write your own shrinks. Internally, the generator type contains, they pair all generation with shrinking. This means that shrinking is inherently, there's a trade-off there. Shrinking is inherently worse than handwritten shrinkers at the cost of, what you gain is developer time and not having to write your own shrinkers. But shrinks can be worse. So shrinks may not perform as well. That is like an important trade-off to think about. And Hedgehog represents shrinks a lot differently than QuickCheck does. So QuickCheck will try to shrink by repeatedly applying values to repeatedly applying the shrink function to a list and then doing some sort of intelligent checking to make sure that shrinks are performed certain ways. But in Hedgehog, they can do a lot more because shrinking is centralized, so they can do a few smarter, better optimizations. But shrinks are actually just a lazy tree, so recall that Haskell is lazy, so infinite structures are really trivial to talk about. So it's just a lazy tree, and all you need to do is traverse the tree. It's a rows tree, and each consecutive node is actually the next iteration of the shrunken value. So the root node is the value that was generated, and then the next node is the result of shrinking that once, and then after a certain point, you reach a sort of theoretical, almost fixed point of what shrinking that as many times as you could looks like.
So there's an epsilon that says, okay, you're close enough and we're done now? Or
I mean, if it tries to shrink it several times in a row and nothing changes, then you know. And all values that it's testing, it has to be able to compare for equality, so it can always perform that check. The other thing that made Hedgehog really popular is it has much better output. The output is prettier, it is clearer, and it uses call stack information to actually show you the source where your logic failed. It's pretty cool. I'll show an example of it. This is just an example of some Hedgehog code. We have a gen int list, which is a generator of list of int, and then our list length is anywhere between 0 and 10,000, and then we generate that list. Enum bounded is a generator which for any enum type and bounded type. So an enum type is one which you can enumerate. You can take the successor of it and you can take the predecessor of it. And bounded means it has a min bound and a max bound. So if you compose those two ideas, that means you can enumerate the entire range of values. So gen.enum bounded encapsulates that idea. And because these are ints, you're going to generate any integer between, min bound and max bound of an int. And then you've got the same prop reverse, except these are, a gen int list. So it'll generate like a list of ints and then check the reverse stuff. And then here is where, in GHCI, I, checked that this property actually held. So let's do what I do best and write some really bad code. So I'm going to write my own reverse function. This is called faux reverse, and it takes a list of A's, and we're going to reverse that list, except it's going to drop a random element somewhere in the middle. So first we have SX, which reverses the list. We divide the list by 2, and then we split the reverse list, and then we combine the left-hand side of what we split with dropping one element somewhere in the middle, which obviously is not going to give us what we want. So this prop faux reverse is basically the same property as before, except we're using a different reverse function. If you compare the two. Does that look basically the same to you? This prop. Everybody agree? Okay. So let's actually test my really bad code. So if we do check prop faux reverse, we get some really, really nice output. Failed after 2 tests and 11 shrinks. So notice it actually shows my source code. It shows the source code of that test, and if you look here, you'll see that like under certain values, it will actually show you what values it generated and shrunk to. So here, x's is the min bound. Like it's a singleton list with just the min bound of an integer, and then it'll failed. Left-hand side does not equal the right-hand side, and it's showing you here that the left-hand side is the empty list and the right-hand side is this, which makes sense because we dropped a random element in the list somewhere. So it would make sense that we have one fewer element. And then the really cool thing, other than this really pretty output, is that you can actually reproduce the errors. It will give you the seed and size, so you can actually in GHCI, you could copy paste this, and you'd have to replace property with the name of your property, but it would actually give you the exact same output, which is really useful. In fact, I've done this before where I actually take failures and turn them into unit tests. So, anybody have any questions about that? Okay.
Well,
yeah.
What does the in the code that's writing line 30, 31, 32, 33, 34, it says failed, and then the first line under failed is dash or minus the empty list. So that's just saying like the dash and plus are only to indicate like. So you see after failed, it has in parentheses minus LHS does not equal plus RHS. Those you can think of those as just labels. So it's just saying plus corresponds to the right-hand side of the equation, and minus corresponds to the left-hand side. So it's saying the left-hand side, which is the empty list, does not equal the right-hand side. And you can see that X is when we ran the generator, probably generated something larger than that, but it was able to shrink it to a case where we can tell, where we can obviously tell like, hey, something's wrong here, and it's precisely that we're dropping a random value when we do our fake reverse. Does that make sense? Sure. And then if I were to copy and paste this thing in GHCI, I would say recheck size 1 blah 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 over 2, and then
you would property. Instead of property, it would be prop underscore faux reverse, and it would give you the exact same output.
Okay, but, I mean, that's cool, but why wouldn't it just go ahead and put in the property that you're testing against? And
That might just be a problem with their pretty printer.
okay,
That it's I'm not sure if that'll still do that, but I don't know if it tries actually to capture the name of the property. I know I have seen it do that, but I'm not actually sure what governs whether or not it prints out, property or the name. And then we can, obviously we can check that, the min bound of an int is that number, and that's just like what it was shrinking toward. It's completely arbitrary whether that is. In fact, the fact that it shows int.min bound just proves like that should be an indicator too that it's probably irrelevant what that number is, which is indeed the case here. So another property that we might want is if we have a reverse function, it should preserve the length of the list. Note that this doesn't actually check whether all the elements are still the same, but it does check that the length is the same. So again, we're testing with our faux reverse, and we say, from our previous one, we had a suspicion that it was a problem with the length. We could say, well, if we reverse a list, we should get the exact same number of elements back. And in this case, Hedgehog tells you exactly like, that's not true. And again, you get a recheck. So, does anybody have any questions so far? Because we're about to move on to the next section. Okay. So I'm going to show you real examples of property testing. And this is going to be less talks and slides and more actual code. So if you're using Git or whatever, however you want to get that, but I do have a GitHub link. It's https://github.com/chessi/hedgehog-talk. And you will find code there. If you're using Cabal, a recent version of Cabal, you should be able to follow along just fine with Cabal new REPL. And if you don't want to play around with the code yourself, you can always just look at it. I like to look at code. I think it looks nice. Okay, I'm just going into this directory real quick. Okay, so is everybody situated with the code, or do you need a moment? You good? Okay. So we got 5 sort of example modules here, and we're going to go from very simple to a little more complicated. And we're going to start with basic, because that's the basic module. So we've just got some imports here, and then usually when you're working with Hedgehog, these are like the 3 imports you always have. You always want just Hedgehog itself, hedgehog.gen, and hedgehog.range. They have a ton of useful combinators. If you want to look at the documentation, it's on Hackage, and you can go to Hedgehog. The documentation is really good. It's very useful. Talks about how you use certain stuff. There's also hedgehog.range has a bunch of the combinators for actually, constructing ranges and using ranges, which is actually very important. As Atif mentioned, size information is often very important when dealing with generators. And then Hedgehog.gen has all of this stuff, like a ton of different like generator combinations, and then you get into like the default stuff. So you have integral, which can generate some like integral value, integral underscore. You have int 8, int 16, int 32, int 64, so on. Floating point stuff, enumerative types, bounded. There are just a ton of combinators here that are really common things you'd want to generate. So when you have time, you may want to look through it. And when we're using specific ones, I will show you, like that specific combinator. So Hedgehog has a few very simple functions: success, discard, and failure, and they all have this type signature. Monad gen M, M unit, which means they basically do nothing effectful, but success says that whatever property I'm testing, that succeeds no matter what. It's just a success with no further context. Discard. So I didn't really cover this when I was talking about generating, but sometimes when you generate a value, often when you apply a predicate to a generator, so say you're trying to generate some integer such that the integer is even. Well, often the most convenient way to do that is to just generate a random integer, check if it's even. But what do you do if it's not even? You just have to discard it and try again. So that's what a discard is. It's where your generator failed to produce something that it deemed valid just for the purpose of generation, not testing. So it will just discard the value. And then failure is the opposite of discard. It just means I'm hard failing right now, no matter what I'm failing.
Opposite of success.
It's the opposite of success. If we actually run these, I'm just going to comment those out real quick, and then I'm going to do basic.tests, and I have this test function in every module, and you can run these yourself. But this uses template Haskell, very similar to what how a Lisp macros work. But what this discover macro does is it looks for all functions in the module that begin with prop underscore, and it like collects them and runs them. It's pretty cool. So check sequential, and they also have check parallel. So check sequential constructs like a list of them and runs them one in a row. Check parallel will check them all in parallel. Like we'll actually do it multi-threaded. So yeah, I'm gonna run that. And then if we look at this output, so prop failure failed after one test. That makes sense because it just hard fails. Prop success passed 100 tests. Prop discard gave up after 100 discards. So obviously we're discarding everything. And then the failures actually talk about, that like it will actually show the failures, and it will show you like the source location and the resize information, or the recheck information. And then we have more tests. So for these are just illustrating some features of Hedgehog at this point. So we have prop test limit, which is just illustrating that you can modify the number of tests that you're running. So with test 10,000, so instead of the default is 100. So instead of 100 tests, it will run the test 10,000 times. Sometimes this is useful if you know that some failing case is extremely rare, or you may know roughly what the distribution of like your generator looks like. So I've actually needed to up that before because I had a failing test case that occurred less than 1% of the time from my generator, which was uniformly random. And I was dealing with bits, so it's not like I could do anything much smarter. And And then prop discard limit. So you can set a maximum threshold of discards. So that by default, I think the default is either 100 discards or discards match the number of tests you're running. With discards says, okay, I'm gonna try as many times as I can, but once I hit this number of discards, I'm just giving up. And this is definitely gonna give up because we're just telling it, the thing we're running is just discard. And then the test limit here, we know we're gonna hit that because we're passing it success. So if I sort of comment these out and run this again, see how it's taking a lot longer to run? Because, so prop test limit finished really fast because success is a no-op, just does nothing. Prop discard limit took a while because it had to run, a generator, 5,000 times, and every single time it discarded. And then the shrink limit thing failed because so with shrinks, this is demonstrating that you can also modify the shrink limit, and we're telling it, generate some character between lowercase a and capital Z, and check, assert that that value must be the lowercase z. Obviously, this is not going to be the case all of the time because there are a lot more characters than just that. So this is going to fail, and because it can't ever shrink it, it only has one value to give. Now, sorry.
If you have a limit of failures, right? So prop discard limit, right? So
You have a limit on the number of discards.
so discard is really a test on the generator, right?
Yeah, discard. So if you have a generator,
You have like, the way I'm thinking about it is you have a generator that's kind of basically, it must be incompletely specified. So your generator is some code that generates something, but then you have a test against that.
not exactly. The discard isn't really to test the generator. It's more to keep it in check. So generators also aren't complete black boxes. The whole point of property testing is to be very conscious of how your generators behave, and then after you've done that bit, everything else is very easy, is very straightforward. So what discard's place actually is for, I'd say the most common purpose is, say you have, say you want to generate even integers. The easiest way of doing that, that you can probably think of, is just generate a random integer and then check if it's even.
Right.
But what do you do if it's not even? Because then you don't, that's not something your generator said it's supposed to do, so you need to discard it and try again. So that's what discard means. Discard means I didn't generate something that I said I was supposed to, so try again.
So it's testing the generator, right?
It's not really a test of the generator, but you could think of it as that, because if you have a generator that discards too much, that means you've probably written a bad generator.
Right, which is where, okay, if my discard limit is 100,000, right? Okay.
Yeah.
If I ever throw away 100,000 things that my generator, if my generator is supposed to generate cases that are useful, but it's failed 100,000 times.
I'd say if you're discarding more than a handful of times, even with the default of 100, you've probably written a bad generator. Even if you in the first 100, if you generate like 50 discards,
Sure.
that's pretty bad. So if your discards are too high, you've written a bad generator and for like the test case, and you should, or you've just written a bad generator and you should rethink it.
Right.
Because so another way to think of it is every time you discard, those are clock cycles.
Yes.
That's developer time. So you want good generators. The whole point of property testing is you write good generators, and then it should be a lot easier after that. Not automated, but a lot easier. So this is a little bit more of a sophisticated property, but not too complicated. So it's testing that a custom implementation of the takeInd function from data.text is the same as a custom implementation on strings of takeInd, which is a function you can find in data.text. And what it does is it will actually take the it will take like the from the end of the list like n elements. The end of in text is a different type, but we'll do that for text too. So what this does is we have x's, and we generate a string between 0 and 100 in length, and it's any Unicode character. That's what the gen.unicode is. And then we generate a number anywhere between 0 and 100, and then we say let string equal, and of course there's no string takeInd function, so we implement it by we reverse the list, we take the first n elements of the list, and then we reverse it again, which is a terribly inefficient way of doing that, but I don't care because this is a test. And then for takeInd, since we generated a string, text.pack turns the string into text, and then we run takeInd on it, and then we unpack it to turn it back into a string, and then we check that string and text are the same. So if we want to actually see, prove that these are the same, we can reload this, and then we can do basic.takeInd. Basic.test, sorry. So yeah, that was all the discard stuff running. And then look, our prop takeInd passed 100 tests. So that one succeeded, and the ones that we expected to fail failed, and the ones we expected to time out, the discard ones, did time out. So does that make sense? Okay. So the next one that may be pretty useful if you've already thought about this. So an obvious sort of consequence of QuickCheck being around, over 20 years longer than Hedgehog is that there's a lot more code written with QuickCheck than there is with Hedgehog. So the Hedgehog authors thought of this, and there's a Hedgehog, QuickCheck library. So they actually wrote something that can convert a QuickCheck generator into a Hedgehog generator. So if you have a if you have an arbitrary instance for your QuickCheck data type, then you can turn that into a Hedgehog generator for free. And this is just a win for Hedgehog because it just makes it easier to convert stuff. And also, if you're importing a library that defines an instance, say it's not necessarily even your own code, say it's just something that, it has an arbitrary instance, say in the QuickCheck instances library, and you don't have to write any code or have already had some QuickCheck code. You can just import that library and run that without having to write a generator, assuming, that generator matches the behavior you want. So, and there's nothing like super complicated here. So it's just the same old, reverse is the, the identity function. So if you reverse it and then reverse it again. So if we do QuickCheck.tests, we should just get, so in that time it generated 100 random lists for each of those and checked that reversing them, and then reversing them again gives back the same list. So the other thing to note is runtime errors. So what if you tried to throw an exception in the middle of one of your functions? Well, Hedgehog is really smart about that. It will actually catch the exceptions and say, like, this failed because it threw an exception. It did not return, a pure value. So we can write this really silly-looking filter function that So filter takes a function from A to bool in a list of A's, and it will only keep the things that satisfy the predicate being A to bool. So if you apply that predicate to an element and it returns true, it will keep that element. But this filter function is weird because its first case is if there are 5 things in the list, I'm going to say, no, that's too much for me to filter. And I'm going to throw an exception. I'm going to say, error, 5 things is too much. And then the rest of the filter function is completely normal. But obviously, if we have more than 5 things, it's going to throw an error. And then this myMaximum function is similar to the maximum function, but it's not total. The reason it's not total is because it doesn't actually take care of empty lists. So if you have a generator for a list that could possibly generate an empty list, what will happen is it will fail at runtime because you're not taking care of that, so it'll have to throw an error. So let's look at a few cases where we actually, like the consequences of good generators are apparent. So this prop equals, we generate a list between the size of 1 and 100. That 1 is really important because if the list is of size at least 1, then it can never be empty, right? So if it's empty, we won't really have a problem. Of course, it's recursive, so we'll have to get to the empty one anyway. But you see my point. That could actually apply to other situations. And then this prop assert says, if we filter, if we filter based on, everything equal to 0, and we expect that to be empty, then we're, asserting that that's the case. The reason that this doesn't make any sense is because we're generating an integer anywhere between, min bound and max bound. So of course, like a lot of those numbers are not 0. It's going to fail. And then here, we're most certainly going to throw an exception pretty quickly. So we can't actually generate a list of size 0, and we're going to see like that, the list, the default like base library maximum is equal to, has the same behavior as our maximum. That should be my maximum. And then we have our test function. So if we do exception.tests, we'll actually get a few problems. So prop equals and prop assert, those were fine. But the one that we, were guaranteed to throw an exception, we got an exception. And Haskell's default exception when you don't handle all cases is non-exhaustive patterns in function myMaximum. Non-exhaustive patterns in function, and then it will give you the name of the function. And it throws like a pattern match fail exception. So Hedgehog is actually, it's smart enough to catch exceptions and give you context around them and still show you the source location where the exception was thrown. Any questions so far? Okay. So this is one of the coolest things. One of the cooler things Hedgehog can do. In this module, it's kind of long, but it's very simple. We have a really simple like token language. Say we're building a Lexer and we have a ton of tokens that make up our language that represent either terms or specific things. Not typically terms, but so this is our token type. It's got a bunch of different constructors. It can either be an int, a double, an assignment, an addition, like plus equals, a tvar is like a variable name, a left paren, a right paren, a plus operator, or some kind of separator. So we have this render token function, if that makes what any of these represent clearer. So we have an int. So a token, it will take a token and produce some text. Makes sense? So we turn the int inside of the tint to text. The double we round to 6 decimal places. Then we have the assignment operator, the plus operator, the plus equals, variable names. We don't have any substitution for those, etc. I'm sure those are all very clear. And then we have a pretty printer for like a list of tokens. And then now what we're going to do in this module is we're going to have a pretty printer for a stream of tokens, and we're going to have a parser for a stream of tokens. And then we're going to use a Hedgehog combinator to prove that these things round trip. And by round trip, what I mean is that if you pretty print a stream of tokens, and then you parse that into a stream of tokens, you get the exact same thing back.
Except for white space.
Yeah. Yeah. So, so we have a white space parser that just consumes white space. It has type. We're using parsec for this, and the parser type, it's consuming text as its input type, and parser unit means like whatever it consumed, it discarded it. So obviously we don't want to keep white space. And we have a parse int, parse double, parser for variable names, and then parse token. This choice combinator, it says give me a list of things that I could parse, and I will try each of them sequentially, and if I fail, I will backtrack and try the next one. So it's a very easy way to sort of compose these parsers, and then we can do the same thing. We can actually use that with some very simple combinators to, instead of parsing a single token, parse a list of them. So we consume white space, and then every time we consume white space, and then we consume a token. And then we have this parse function, which takes a piece of text, and we either get a parse error, which is a data type in parsec, or we get a list of token. And it says we're done whenever we reach the end of file character. Now here's where Hedgehog comes in. So we're actually we have a function to generate a list of tokens. So a single function to generate one token, and here we generate a number. We can generate int. So that gen.choice combinator works very similar to the parser, parsec.choice. It will randomly pick one of them. And so it doesn't actually need to try them because you're not parsing, you're producing something. So it will just like pick a random one and do that. They all have to have the same type, of course. But so we generate a double, or we generate any of the other tokens. And then round 6 just rounds a double to 6 decimal places to make sure that the one we randomly generated matches what we expect. Notice that in this token, we're not doing any like validation or like making sure that our stream of tokens is well formed. That's not the point of this exercise. And then gen tokens, very simple Hedgehog combinators. We have a list, and we generate tokens between 0 and 100, and we give our generator gen token, and then our prompt trip. So we want to run this test 1,000 times, and then we generate a list of tokens, and then Hedgehog has this tripping operator, and you give it a value, and you give it a way to encode that value into some type, and then you give it a way to take that type that you encoded it into and decode it into something else, and it will check that they round trip. The type signature is a little more complicated, but I don't want to confuse anyone. But basically, it checks that it checks that if you encode it and then decode it, you get back what you put in. So if we do round trip tests, past 1,000 tests. So we have like a very simple token expression language and then encoding it and then decoding it. There was a more complicated example I wanted to show where I actually was writing out, like an implementation of the simply typed lambda calculus, but I didn't have time to do that. It was actually very short, but I didn't get around to actually writing all the Hedgehog stuff for it. So the last example I have requires a library other than just QuickCheck, other than just Hedgehog. And I'll show you that real quick. So this library is called Hedgehog Classes. This is a library that I wrote on top of Hedgehog. And if you recall back to when I was talking about how I think type classes should be lawful, a lot of people agree, and there are a lot of type classes in Haskell that do have laws, and your instances should abide by those in order for APIs to actually be sensible and bug-free. So you have guarantees about the behavior of certain functions. So instead of Hedgehog will eat your bugs, it's Hedgehog will eat your type class bugs. So if we actually go down to the documentation here, it's hedgehog.classes, and it also has pretty decent documentation, and there's a lot of support for things like binary encoding, decoding, making sure that round trips, testing, equality, monoidal properties, ordering, enumerations, semigroup stuff. It can test that if you have something that you can encode to JSON and then decode it, that round trips. There's a bunch of stuff here, and you can look at it if you want. So if we actually look at class.hs, so we have our trio of imports that we always have with Hedgehog, hedgehog.gen, hedgehog.range, and we import hedgehog.classes, and then we've got some other imports from standard libraries. So I wrote out some generators here already. Gen either, it takes a generator for A and a generator for B, and it has an equal probability of either producing an A or a B. And then a set is just like an ordered set of things, and a map is a map, it's a dictionary. And if you want to look at those, we've already gone over the combinators that make this up. So I have a generator for a string, and obviously because I'm generating a string, I need to tell it what sizes. So I'm generating a string anywhere between 2 and 6 characters. An int, and then I have a few generators of different, arities that are there to satisfy Hedgehog classes. So, and then I have the test here. So for set of int, I'm testing things like eq-laws, monoid laws, and then there are more complicated things like functor, applicative, traversable, bifunctor. If you don't know what those mean, that's fine. You can look at them, but they're just type classes that have certain laws, and if you implement them for your type and you don't obey the invariants, then people will use your code and won't get the expected behavior. So if we run this, if we do class.tests, and the output of this is a little more verbose. So for set int, it will show you for each, not only for each type class, but for each law of that type class that it passed tests that show you that it has the expected behavior. And in the spirit of Hedgehog, it also has really good error messages. So I created a type called badList, and I gave it a foldable instance that does something bad. So in Haskell, everything is lazy by default, right? So the foldable type class has a left fold, and it has two left folds. It has foldL and foldL prime. FoldL prime means that it accumulates strictly. So instead of avoiding the computation of your value every time it does an accumulation when it's folding, it will evaluate whatever you just tried to accumulate. But if you notice here, so bad list is just a new type around list. If you notice here, the foldable instance, I say fold L prime is fold L. So that won't match the performance characteristics that I want. This is different than, you know, the types not matching up or, you know, having a nonsensical instance. This is actually about, you know, performance characteristics being different. And there's like some clever machinery in Hedgehog classes to make sure that this works. So let me make sure I save that. So if I do. So notice I just got a failure. So context, your implementation of fold L prime is not strict. That's pretty cool, right? So it was actually able to like figure out that you weren't accumulating strictly. And your test suite failed because of that. So now if we comment out that, and then I also wrote this type that called bad eq. And you can do more clever things than this. You can make like things like reflexivity, or well, actually, this will make reflexivity fail. You can make other like eq laws fail, but this bad eq one, it has one constructor called E1, and I made equality always return false, which is not what you would expect. And the generator can only do one thing. It can just, you know, return the single constructor. There's no values to generate. There's nothing random about it. It needs a show instance. Deriving show. So from these, I get a different failure. When testing the reflexivity law for the eq type class, the following test failed. A equals A where A equals E1. The reduced test is E1 equals E1. The law in question is the reflexivity law, and it, you know, says what that is, and it also gives you the recheck. So, yeah, I said this is obviously what would make reflexivity fail. So, yeah, so that's that is Hedgehog classes. It's very useful specifically for Haskell. However, the rest of the concepts in the talk are useful in a multitude of languages. If there were a port of Hedgehog classes for something like OCaml or any language that implements some kind of like has a very pervasive sense of lawful type classes or interfaces, you know, a lot of languages don't really care about laws in their type classes because they have other things to worry about. That is the gist of my talk. So, does anybody have any questions? Well, it's not really a gist. I just talked at you for like an hour. But does anybody have any questions? Any questions from online?
So let's see, we've got a couple. There's one is, so he says, this might be a naive question, but if we're using arbitrary type classes, do we explicitly define the instance? What if we have a user-defined type that has a shrink operator as well?
I'm not sure I understand the question. Could you repeat that?
It says, for using arbitrary type classes, do we explicitly define the instance?
Is he talking about the arbitrary type class or arbitrary the word type classes?
Yeah, I'm not sure.
Could you rephrase the question, please, and then I'll be happy to answer it. I'm not sure I understand.
All right, we'll wait for it. But there's another question too. So with property-based testing, do unit tests end up becoming regression tests of failures?
So
Property-based testing failed on?
So that's a good question. So yes and no. So you can take failures from property tests and turn them into unit tests, which is very often what I do. However, unit tests do still have their place. There are some times where it's sort of difficult to have like a declarative output for how something should behave, or like a declarative property. For example, a coworker was writing some interface to the InfluxDB line protocol in Haskell. And it was actually something that was a little awkward to, generatively test, because the output, he would have had to write a parser for their line protocol, that would check a lot of invariants. So it was actually more practical to just write a few unit tests, than it was to write a parser for that. Of course, this is a situation where ideally you'd want generative tests, but there are also examples where property tests just don't work and unit tests still need to be around. More on that point, one thing that I didn't get to talk about in this talk because I didn't have time was state machine testing. So Hedgehog has support for state machine testing. And if you're familiar with automata theory, you'll recognize basically what this is. But the idea is that in the real world you have things that are very effectful. You're not just running pure code all the time. You want to model your business logic in a way that where you can actually test it. But this has historically been pretty difficult. But the Hedgehog authors actually came up with a really clever way of doing state machine testing. And I don't want to talk too much about it because it's pretty complicated and probably deserves its own talk. But the state machine testing in Hedgehog has been used to do things like test the WordPress API. So, for example, there was someone at the Queensland Functional Programming Lab that re-implemented a large portion of the WordPress API and used the Hedgehog state machine testing to actually find out that it wasn't thread safe. So that's one thing. Another application that is notable is that someone set up a full web server that accepted tons of concurrent requests and did a bunch of jobs, and it was actually they used it to prove that this web server was actually handling these things correctly, and it wasn't like a mock web server. It was a real web server using real industry tested libraries, which is very cool because real production code is often very at the point where it's touching your users, it's often very stateful and concurrent, and there's a bunch of different concerns there that you might want to test. So, are there any other questions?
No, that's it. No.
Okay. You guys have any questions? Okay. Well, I think we're done then.